So we're just going over homework. And when we look here at number 3, it's super important that you understand the difference between what's going on in this column and what's going on here. Who can explain to me the difference between those two columns? It's a big deal. I know they look different, but what do they mean? How are they different? You want to go for it, Catherine?
First column, x has a given value, which is 5. And then in the second column, it's as x approaches 5.
Yeah, that's a great way of phrasing it. So in this first column, my function, when 5 is the input, has an output of 1. In this second column, as x approaches 5, from both the left and right, it has a value of 6. So it's kind of like if I were to have a hole or a jump. So if my graph is approaching 6, but it has an output of 1. And we have to understand the difference between the value of the function at that point and the limit, because the limit is a conversation about what's happening as I approach something from the left and right. So we'll talk about that limit. Where's the function going? All right, Ricardo, which one did you want to talk about? B? Okay. So as x approaches 5, I want to know the limit of h of x divided by the limit of g of x. So when I look here, what I care about is h of x as x approaches 5. That's going to be that there. So that limit output is going to be 5. And then the limit as x approaches 5 of g of x. So what I care about here is -1. So this is going to get a -1 underneath. So that's what that expression is worth right there. So when I come to my next portion, this here, I'm just asking for when 5 goes in, what comes out? Ooh, that's a mistake on the key, isn't it? Because this should be +1, not 3. I must have been looking at H. So go ahead, Ricardo, put a smarty up. That should be 1. Make sure you check your work.
What about A?
Okay, let's double check A. So it's twice the limit as x approaches 5 of f of x. This should be 6. That's okay. And then as x approaches 5 of g of x should be -1. So that's 12 plus -1. So that one's okay. That one's 11. Grace?
Could you go over 7 for A and
Sure.
B?
All right. So any questions on 4, A, B, C, and D?
No.
That was pretty okay? All right. So for 5 and 6, that's our piecewise function. Check your answers. Anybody want to go over any 5 or 6 questions? Things you do or do not understand? Ricardo, did I make any more mistakes? You didn't do it?
No, I don't really understand how to do that.
Okay.
Like
Which one, 5 or 6?
5D,
Okay. Did you say B or D?
D,
Okay. So for 5D, when we look at this, so our piecewise function divides my values of x. So when x is smaller than -2, I'm going to go ahead and use the function of 1 over x plus 6. That's this one here. When x is greater than or equal to 2 and less than 0, I'm going to go ahead and use this function 2 to the x. When x is greater than or equal to 0, then I'm going to go ahead and use this function x squared minus 4. So as I look for whatever limits I'm talking about, I need to first of all look at what the value of the limit is and what it's approaching. And then sometimes I need to look at from what direction it's approaching, the positive or the negative. So for D, X is approaching 0, and it's approaching 0 from, guess what? The positive and the negative values. So what I need to do is put this value 0 into each of those functions and see if they match. If they match, then that's my limit. If they don't match, then I can say the limit does not exist. So when I put 0 into, as I'm approaching 0, I put 0 into 2 to the x, I get 2 to the 0, and that is equal to 1. Anything to 0 power is 1. When I come over here, I have 0 squared minus 4, so that's going to be negative 4 as I'm approaching from the positive. So this is from the left, and this one is from the right. And as you can see, these values don't match. So when somebody asks me what is the limit, I'm telling you it doesn't exist because they don't meet up at the same place. What else you got? Sure. So when we have this graph to use these limits, the limit as x approaches negative 3, so here's an x value of negative 3, and if I want to see what the limit is, I'm looking at what happens as the values come from both the left and the right. Because there's no symbol here, I have to consider both, that my limit's coming in at the same time. What I mess up on?
That's not what matches our homework.
Yeah, because we had f and then f of x in parentheses too.
Okay. So you guys had f of x. Yeah. For both of these. Yeah. So we changed that. And we'll do both. I'll show you what they both are. All right. So we'll start off easy. As x approaches here, we have this value of 1, right? So that's going to be positive 1. And I think you can see on my key where it says f of x next to it, that answer is 0. So what ended up happening was when we did it originally, we put this in, and then we went back and thought that might be a little too confusing and too hard. But let's talk about it anyway. If I put negative 3 in for that x, my output, negative 3 in, output here is positive 1. So then I wind up finding the limit as x approaches positive 1. So as x approaches positive 1 from the left and from the right, that's why that one is 0. And that's what you can see on the key right next to it. So it's funny, we did it, and I made all my copies, and then Ms. Holdaway came and said, I think this might be too confusing to them. And we actually had a discussion about it, and I had already made the copies and forgot. So that's on me. So Carrie, you can put a smiley up. Sure. So when I'm talking about a composite function, when we have f of x, and I'm asking you for the limit as x approaches negative 3, what I care about first is I dive into the center. So what is the function of an input of negative 3? So when I put a negative 3 into this function, do you see how I get a 1 out? Okay. So my output, f of x, is equal to 1. So then this here becomes a conversation of this here has an output value of 1. So now I want to know the limit as x approaches negative 3 of f of 1. Right? So and is the limit, so I'm going to be looking at this output value of 1. So when we look f of one, so limit of, so then this becomes f of one, and then that's where I'm going to be looking here, and that's why it's 0. So we can do the same thing here. As x approaches 0, my limit is equal to 1. That's the easy one. Let's come over here and do the hard one. As x approaches 1, then that makes, as x approaches 1, that gives me an output of 0. When as x approaches 0, that's where I have an output. Should I say that backwards? As x approaches 0, it's 1, and as x approaches 1, it's 0 again.
Aren't you supposed to plug in the 0 for x?
So, let me get this, let me make sure I'm not.
Because you plugged in the -3 for the other one.
So as x approaches 0 here, so yes, this should be 0. So as x approaches 0, that's where I have an output of 1. That's what we have there. But now that here, I put it in the wrong spot. Now that my output is equal to 1, I'm going to do as x approaches 1, and that puts me back again at 0. Do you see why we decided the f of x's were too confusing? All right, Catherine.
On number 6, can you do letters B and H?
B. Number 6. Okay. So my conversation here is between pi and 2 pi, right? So if I look at my number line for my input values, I have pi and I have 2 pi. And if my value is less than pi, I'm talking about the sign of theta. If I'm in between pi and 2 pi, I want the cosine of theta. And if I'm bigger than 2 pi, I want the tangent of theta. So you asked for B?
Yeah, I don't need it anymore. I saw that it's less than or equal to. I didn't see that it equals to.
Yeah. Did you want D too, or are you okay?
No, I think.
Okay. Anything else? Anything else? Go ahead.
Can you do, B at number 5? And then to-
B on number 5?
Yeah.
Sure. Okay. So I'm looking at x approaching -2, and I'm coming from the negative side. Because I'm coming from the negative side, I want this function here, 1 over x plus 6. So I'm going to do 1 over -2, and that's going to be plus 6. Is that okay? Oh, wait a minute. My plus 6 isn't in the right spot. That's better. 1 over x plus 6. I need to fix that on my thing. There we go. So do you see why it's 1/4? Put it.
Eight.
8. B. Okay. So use the table to find the limits. As Catherine told us, make sure we understand how it's written on the left-hand side is whatever input value for our function f, g, and h gives us that specific output value. What's over here is the limit as x approaches that, and you see it's different every time. So we need to pay attention to what it is we're talking about. All right. An input of 3 on G gives me an output of -4. As x approaches 3 on H and F, I'm finding that product. So my limit of my H function as x approaches 3 is going to be 3. And the limit on my F function as x approaches 3 is going to be 1. So it's -4 plus 3, -1. Sound okay?
Yeah.
Okay. Yes,
Question about on the test.
okay.
The graph part. One of the questions was, is it continuous? And I thought continuous meant that it goes on forever.
No, continuous in a graphing sense, basically, if you put your pencil on it and you went to draw it, could you do the whole graph without picking up your pencil? So it doesn't need to go on in both directions forever and ever. It just means, is there any breaks or holes or jumps or asymptotes in that graph? Does that help?
Yeah.
Done?
But there is a hole at the end of the graph,
Right, but I can,
so
that
that's
just is
what
where
we-
it stops. Do you know what I mean?
Yeah.
If that hole was in the middle, like, let's say that I had a scenario where I had a graph and it went like this, and then it continued on. If I wanted to trace this graph, I can start here, but there's no way for me to get over here without picking up my pencil. If this graph ended here, then there's no need for me to go past that. So did you cover the whole graph? Yes, I did. That's what we mean by continuous. Yeah,
On homework 6D,
on homework 6B, okay? Yeah. So my input value is pi. So when I look here, I can see that theta, when it is smaller than or equal to pi, is going to use the sine function. So all I need to know what the sine of pi is. Isn't that 0? Yeah. Because this is just it. Like, this is just the function. Tell me input of pi, what comes out. It's not a limit question. Same as this, this is not a limit question. We're just talking about what comes out with that input for the function. Okay. All right, so did everybody pick up notes? So last time's class had us talking about calculating limits using algebra. Hey, just like when we did algebra and slope, you don't always walk around with a coordinate plane in your lap for you to plot points and count slope or look at something. So the algebra is quicker, faster, easier, and it's what we need to be able to do. So the number one rule of calculating limits is always going to be to substitute and simplify. So, okay, the limit as x approaches 5 from both sides, we're going to go ahead and put 5 in here, and then 5 in here. And I'm a little nervous because I'm noticing something weird happening. I get a 0 over what the heck? So we got a problem because number one, if I just had a 0 in the denominator, that would be one thing, but having a 0 in the numerator and denominator gives us a situation where we have what's called an indeterminate form. And an indeterminate form is going to be when I get 0 over 0 or infinity over infinity after substituting in to evaluate the limit. That substitution is not going to work. So you didn't think it was going to be that easy where we could just substitute and find the limit. So we're going to get into these more complicated versions of what we are doing. We have some options though. We have some tricks in our tool bag when it comes to manipulating. So I want you to imagine here's our tool bag when we go to work on these limits. And number one is always going to be, can we factor? So I don't know. Let's look at this first example again. If I had x minus 5 in the numerator, There's nothing there I can factor, but take a peek at that denominator and say hello to one of my best friends. What do you see is there? What is that?
Square.
Yeah, it's the difference of two perfect squares. So I know right away that that difference of two perfect squares is going to factor into that. So when I take the limit as x approaches 5, before I substitute and simplify, let's cancel a few things out. Let's take that factor and cancel out. Because now, when I have the limit as x approaches 5, I'm looking at something that I can substitute and simplify into. So what ends up happening is, inside of this tool bag, I've got some algebraic strategies that are going to help me address what my problem is. So I can go ahead and substitute my 5 in, and I can say the limit as x approaches 5 is going to be 1/10, and that is the limit. So you'll remember from your study of rational functions that this represents where there's a hole, where that value is undefined, and I can factor it out. So factoring is just one of our options. We're also going to be able to look for and add some fractions to find a common denominator, and that will end up changing things. We're also going to look for and find situations where I need the conjugate. So the conjugate is a value that brings about the difference of two perfect squares, because I'm using the sum difference pattern, and that'll help me manipulate when I have things like radicals. And then, of course, our trig rules, and I know you are so excited about remembering all those trig rules. And your reference sheet that we gave you last class has all of our trig rules on them. All right, so let's work through some examples. Take a look at number 1. I don't see any common denominators that I'm going to have to add. I don't see any need for the conjugate, and I don't see any trig rules, so it's got to be what? Yeah, so go ahead and factor this and substitute in and see if you can figure out our limit.
Find the curve. The correction is kind of, I'll catch up with you later because we went through that twice today already.
Okay, thank you. Can you explain to Maria about the curve?
Oh, yeah, so, you find your average, right? Where your average is multiplied by 10, that's how much it costs. Huh?
What would you like?
So, whatever every percentage is,
Back. So the number one thing that we want to remember, and we're in the zone where we're talking about factoring, so we dove right into factoring. But the reality is, our step one is always going to be to plug and chug, to substitute and simplify. Because we want to see if it's an indeterminate form or not. When we find the limit as x approaches whatever input value, if there's a chance that it's going to work out, we need to first investigate that. So when I put -3 into x in my numerator, and when I put -3 in for x in my denominator, I need to first simplify to see what ends up happening. So when we do the math, we have -3 squared is 9, -3 minus 6, -3 squared is 9, minus 6 minus 3. What do you see happening? Yeah, I end up with 0 over 0. And sometimes it's frustrating because you're like, we're in that lesson, they're all going to work out like that. But the next time you're looking at a quiz or a test, that might not be the case. So if it can work out, we need to take the time to test to see if it's going to work out. It didn't. So what we need to do then is take a look at and factor. So here I have x, what's this, +3 and x minus 2 over x +3 and x minus 1. Okay, here's a secret. When we give you things like this and these examples, they're designed to work out. So if you're having a hard time factoring, go ahead and choose from these numbers up above to see if you can find the one that's going to make this work out for you. Because once I get rid of that, I'm in a better situation. Because when I plug in, I have -3 minus 2 over -3 minus 1. So when I go to simplify that value, that looks like -5 over -4. So I can say that that limit, as x approaches -3, is 5/4. I was able to eliminate what made my fraction a mess. And I was able to continue working it out. Does that make sense to you? Okay. Is there your question? Okay. So moving on to page 2. So when we start talking about example 2, this may have gotten cut off, but this is a sum of 2 cubes. So when I have the sum of 2 cubes, I know I can factor that, just like so. And of course, that's going to work out. Now, remember rule number 1, substitute and simplify, plug and chug, because that's what they want us to do. When I have -1 cubed plus 1 over -1 plus 1, we know exactly what's going to happen. We end up with 0 over 0. So we don't resort to these techniques until we end up with one of the indeterminate forms, either 0 over 0 or infinity over infinity. All right. So I'm going to go ahead and I'm going to try to factor this. Because it's the sum of 2 perfect cubes, I know I have the same sign, and then I have the opposite sign, and then I have always positive. And you should not be surprised at all that again, these are what? Designed to work out. They're designed to work out. So you need to make sure you have that SOAP, same opposite, always positive, for when you're talking about your sum of two perfect cubes. Now when I go to take the limit, I can go ahead and plug in -1 into x squared minus -1 plus 1. And notice I have a denominator of 1 now, so I have no variables down there, nothing to plug in. So I end up with 1 plus 1 plus 1. So my limit for that is going to be 3. Those are examples for factoring. Thumbs up if they make sense to you. Rock on. Okay, here are our examples for common denominators. And I know I need a common denominator because I spy with my little eye a fraction that needs to be added. Now again, I know I need to do that because I'm in the unit of indeterminate forms, and I know that that's going to be 0, 0, or infinity over infinity. But guess what? I still have to do what? Say it. I still have to substitute and simplify. 1 over 0 plus 4 minus 1/4, all over 0. It's itching at me just to see that 0 in the denominator. Oh my goodness. Not allowed to do that. I end up with 0 over 0, which means I'm going to have to get some new math. Now, we haven't really talked about finding common denominators. I'm hoping you remember it from your Algebra 2 and pre-calc days. Those are my factors. Before I can add those fractions, they have to have a common denominator, meaning all the factors have to match. Whatever one fraction's missing, the other one's got. Does that make sense to you? So here's an x plus 4, he's a 4. He needs a 4, he needs an x plus 4. We bubble wrap each expression to keep them nice and tight because we're not taking any of these 4's out and we're not messing with the x plus 4. Got that? Okay. So this guy needs a 4. So we're going to multiply this fraction by 4 over 4. That's going to give us 4 over 4 times x plus 4. When I did this with my Algebra 2s last year, the one guy's like, oh, why don't you cancel that out? Because I just put it there. I'm unsimplifying the fraction so that the denominators match. This guy needs an x plus 4 over an x plus 4. So this becomes minus x plus 4 over, do you see my common denominator? Say yes.
Yes.
Okay. Don't forget that's all over our dear friend x. So now when I go ahead and I combine these fractions, I have 4 minus x plus 4 all over 4 times x plus 4 all over x. Anybody nervous about that x hanging out in the denominator? Don't be. Now I have 4 minus x minus 4 over 4x plus 16 all over x. I take that back. I want to not distribute this. I'm hoping it'll cancel out. You okay with me leaving that as is? I need more paper. Do you see my 4's canceling out? Is my x positive or negative? Good. So I've got negative x because positive 4 and negative 4 canceled out. Negative x is over 4 times x plus 4. And instead of dividing by x, I'm going to do it this way. Because we don't divide fractions, we multiply by what? The reciprocal. Here's me and Keith Berkeley over reciprocal, remember? Are you still worried about that x? No, because what's going to happen? Yeah, don't forget about your negative. So now you have negative 1 over 4 times x plus 4. Now that I have that, we're going to go get what? We're going to go pick up the 0. Why 0? Because that's where x is going. That's what my input value is approaching. You okay with that? Hey, all this is algebra 2. You remember it now? Is it coming back? Negative 1 over 4 times 0 plus 4. Sounds a lot like negative 1/16 to me. Sound okay?
Yeah.
We found our common denominator. Okay. Our next two examples are going to involve the conjugate. Take a look at them. How do you know it's not factoring? Because there's nothing to factor. Thank you, Kara. Was that you? How do you know it's not a common denominator? Say it with me now, come on. Because there's no fraction. All right, so when we start looking at this, it's got to involve the conjugate. Okay, rule number 1. Now, even though we know what unit we're in, and even though we know these are our indeterminate forms, good habits are good habits. So what are we going to do first? Substitute and simplify. By the way, the circled S means simplify. All right, so the limit as x approaches 0 of the square root of 3 plus 0 minus the square root of 3 all over 0. So I get the square root of 3 minus the square root of 3 over 0. Uh-oh. Every time. All right, so now we're going to check out what happens with a conjugate. The conjugate is defined as a value that you can multiply to eliminate basically what you don't like. We use it with complex numbers to get rid of I, because we can get rid of i's in that way. We can get rid of radicals in that way. And we're relying on our sum difference pattern from factoring. If I say this minus this times this plus this, in your head, do some first, inner, outer, last. Your first terms are going to multiply. Your inner and outer terms are going to be opposites. They're going to be a 0 pair. One is going to be positive, square root of 3 plus x times root 3. The other one's going to be negative, square root of 3 plus x, root 3. So what's going to happen is they're going to cancel out. And then our last terms are going to be root 3 times root 3. The problem is we can't just go around multiplying whatever we want. We have to follow the rules. So whatever we do to the top, we have to do to the denominator. That, what you see in green, has a value of 1. Anything times 1 is itself, I haven't changed what it's worth. I'm changing how it looks, but I haven't changed the value of that number. That's the power of our multiplicative identity. That's the power of one. So when you're back in algebra class learning all these properties and you're like, these are stupid, they don't make sense. Okay, here you go. Without this, we wouldn't have been able to come up with a common denominator, and we wouldn't be able to work with our conjugate. All right, here we go. Our first terms, bubble wrap them if you need to, because the square root of 3 plus x squared is going to be 3 plus x. Hold on to that for a minute. Does that make sense to you? Do you want to see that? Or does it, or the square root of something squared is that thing? You okay with that? I'm getting some thumbs up. That's good. All right. Do I need to write out my zero pairs, or do you trust me that they're zeros? You trust me. Thank you. Are you okay with -3? Yeah? Exactly. That's exactly what it is. It's the difference of two perfect squares. And it's funny because they factor into and multiply into each other. Our sum difference pattern and our difference of two perfect squares. Here's the deal though. The denominator is not so pretty. We still have all this stuff happening in the denominator. So we wind up with x times the square root of 3 plus x plus, and then it's up to us whether we want to, I think maybe I'll leave it as an algebraic expression. Just to show you x is times all that stuff. And I'll tell you why we left it, and you'll be able to see it super fast. When I go to simplify my numerator, positive 3 and negative 3 cancel out, and that leaves good old x up there by himself. And you're worried about that because x is equal to 0, and you're like, oh no, what are we going to do? X is equal to 0. And you're like, relax, wait till you see what happens to those x's. What's going to happen? Yeah, bye-bye. See you later, Sally. Now when I have 1 over the square root of 3 plus, I can plug in my value, 0, plus the square root of 3, and I can have 1 over 2 roots of 3. And then, of course, we have to rationalize that denominator. Because we're rule followers, everybody. Square root of 3 over 6. Do not dare cancel out that root 3 with that 6. Those are not friends. Square root of 3 is not friends with 6. How we feeling? Yes.
So you're saying that like the 3, so the 0 can't be that, so it's square root 3 plus square root 3. So there's 2 in the denominator. That's what
Right.
it's done?
So this simplifies to just the square root of 3. And then because my radicands match, I can add them. So here's 1 square root of 3. Here's 1 square root of 3. You have square root of 3. Our square root of 3 together we have 2 square roots of 3. Okay. Now here's this craziness. Amidst all of this, here's another example that we missed. You're like, wait, there's no room on my paper for him. We'll come do him another day.
Really?
Well, he's solvable. Is it really bad? If you want to try this one on your own, Kira says it's not solvable. But when I did it on my own, I got 1/4. So if we don't agree, If we don't agree, that's a smarty in it for you. All right. Here's what I want to show you that I think is pretty cool with what it is that we're doing. So I'm going to try to take a look at the front, the very first problem that we went over. Hey, check it out. That's the graph. And maybe I want to make it a little darker so you can see. Can I do this? Maybe not. Now let me make it darker. What was that? 2.5? Yeah, I'm trying to make it darker. Oh, it didn't work. A little bit darker. Did it go a little darker? All right. Hey. Don't start talking. Listen to me. Look up front. So on Desmos, what we can do is take a look at that graph, right? So here's what's important for you to see. This is the graph of our rational function. I've got more x's in the denominator, which means I got a horizontal asymptote of y is equal to 0. I've got a vertical asymptote right at 5, right at -5, right? Where, think about our two factors, where my one factor goes to 0. The limit that we talked about, do you see it here? Do you see that? When x is equal to 5, what do we have? No. What do we have? When x is equal to 5, what do we have? A hole! That's the hole that we eliminated. So when we were talking about getting 0 over 0, when we plugged in our limit, that's what the hang-up was. Now, you couldn't see it until I highlighted it, until I showed you what that ordered pair was, because what ended up happening was we canceled out x minus 5 from the numerator and denominator. We had x plus 5 in the denominator, so that explains this horizontal asymptote at x equals -5, vertical asymptote. But when we look at that point that screwed everything up, we removed him. He was a removable hole. All right, take a look at the next one that we factored. Ready? Here's x squared plus x minus 6 over x squared plus 2x minus 3. This was what we removed. We factored out, did we factor out x plus 3? So that x value of an input of -3, that's where we were getting our hole. There he is. So when the function exists without that factor, it's not a problem. We still have our vertical asymptote, we still have our horizontal asymptote, but it's this point that we were able to factor out. Kind of cool, right? All right, let's look at this one. Here's our common denominator one. X was not allowed to be equal to 0. We can see that right from the very beginning. But by using our common denominators, we were able to factor out an x. And now this hole here isn't a problem for us. We removed it so we can still find the limit at that point. Here's our conjugate. It's a square root function. And you can see it. And where is our hole? There she is. That's what we removed by using the conjugate and factoring out and canceling out that x. How cool is that? So as we continue on, we're going to start talking about, oh, hello, sine of x. And we're going to be talking about some trig fun with sine and cosine. And we're going to pick up on that with the second half of the notes next class. So what I want you to do is on the back, there's a conjugate problem. Let's go ahead and pick up, and I want you to do a conjugate problem on your own. Ready? I want you to, let's see. Come on down, and I want you to try with your partner 1 and 2. Go ahead.